A huge thanks to Brian for sponsoring this video. Good morning, fellow mathematicians. Welcome back to the last video of 2025. We are civilized and we do not enjoy fireworks over here, but we can still end the year with a bang, with an integral. We are going to take a look at the integral from 0 to 1 of 1 over the rested radical, that was on purpose, the nested radical of square root of x plus square root of x plus square root of x and so on up until infinity. It's actually a banger. Try it out for yourself. I really love this integral. Once you got a solution, post it down there in the comments below. By the way, this video has been sponsored by the wonderful people over on Brin. More information at the end of the video. Just hear me out. They offer an amazing service to the STEM community. Check it out at the end of the video, and now we are going to dive right in. So as always with infinitely nested radicals, we are going to check for convergence at first. No, we are not. We are just going to assume that all of this converges in our interval of choice. But what we are going to do is we are going to rewrite this denominator down here a tiny little bit, because infinitely nested stuff is a bit fiddly to work with. So we are just going to take the recursive approach here. So at first we are going to say let some variable t be equal to our nested radical that we have right here. So square root of x plus square root of x and so on. Now what you are going to notice is that since this right here is infinitely nested, if we were just to take a look at this part that we have over here, so just this tiny little part here, you're going to notice that this part is exactly t once again. So this right here is t. So overall, by a recursive relationship, we are also going to get by the substitution that our nested radical, our denominator that we have down here, is equal to square root of x plus and all of this, t. But we also know that our entire denominator is just t, so this leaves us with this relationship that we have right here. And this is something that we can actually work with. So let us do this, shall we? So the first thing we are going to do is this right here is not yet a substitution in terms of integration. So what we need to do is we need to find an explicit relationship for t with respect to x, and then we can plug it in and then resubstitute stuff. So what we are going to do is we are going to solve all of this for t, starting off by squaring both sides, getting rid of our square root at first. And now we are going to subtract the t and the x on both sides, giving us just a quadratic in t, namely t squared minus t minus x is equal to 0. And by using the quadratic formula, we are going to notice that there are at first two solutions, t1 and 2, being positive 1/2 plus or minus the square root of 1/4 plus x. So t is with respect to x. Now hear me out. Those are all positive square roots. There is no other branch in here. It's just a principal branch of everything, because there's no negative sign in front of our nested radical. So we can just conclude from this that we are going to take the positive branch right here overall. And this right here is t, which is equal to our nested radical, which is equal to our entire denominator. So we can rewrite our entire denominator as being just the integral from 0 to 1 of dx divided by 1/2 plus the square root of 1/4 plus x. And now we are just going to be left with an integral over basically just something square root expression. And now we can start substituting and getting rid of everything. Now the easiest way I found to solve this is to rationalize the denominator at first, because dividing by a square root in some kind of way is a bit fiddly, especially if there is no square here. If there were a square here, we could just use, for example, a substitution tangent of phi, for example, and then solve using the fundamental theorem of trigonometry. But this doesn't work out here, so let's rationalize the denominator and then see where this goes. So we are going to multiply both top and bottom by the conjugate. So that means multiplying both sides, or numerator and denominator, by 1/2 minus the square root of 1/4 plus x. And the same thing down here, doesn't change anything about the expression, minus square root of 1/4 plus x. Obviously the x is going to go over here, because it's with respect to everything. Okay, And now it's kind of easy to see that this right here is just the difference of two squares down here. This is how rationalizing the denominator works. And 1 times everything up here is just the thing up here. So we are going to end up with the integral from 0 to 1 of the binomial formula, difference of two squares down here. So this gives us 1/4 minus the square root of 1/4 plus x squared, which is just 1/4 plus x, but with a negative sign, so negative 1/4 plus x. And up here we have 1/2 minus the square root of 1/4 plus x. Okay, thus far that's good. Now we can start simplifying the denominator down here a tiny little bit. 1/4 minus 1/4 is equal to 0, obviously, but we get a negative x here, and we can drag the negative sign to the top and change the order of those two around. Let us simplify this a tiny little bit more before we continue with the integral. So integral from 0 to 1 of, and then we are going to get the square root of 1/4 plus x minus 1/2 divided by x dx. And now it's actually rather easy to see where all of this is going. We need to get rid of the square root here. That's just a simple algebra by using a simple substitution. So just let, we already used t. We are just going to say let r be equal to the square root of 1/4 plus x. We have x down here, so we need to solve for x actually to have it with respect to r. So we are going to square both sides. So our substitution is actually just r squared is equal to 1/4 plus x. Implicitly differentiating both sides gives us 2r dr is equal to just dx. And this basically settles everything that we need to do. So this thing right here is just r. This thing down here, x, is r squared minus 1/4. This is what we got here. And the negative 1/2 just up here in the numerator. I left it here because it makes things a tiny little bit easier. If you were to include it in your substitution, you would need to add 1/2 on both sides and then square it. You could do that, obviously, but I'm just leaving this out. This makes it a tiny little bit easier. So let us plug everything in and see where this is getting us. One other note is we need to plug 0 and 1 into everything. Now remember that r is equal to the square root of 1/4 plus x. So if we plug 0 into x, we are going to get the square root of 1/4, which is just 1/2. And if we plug 1 into here, this is the square root of 1/4 plus 1, which is 5/4, so the square root of 5/2. Maybe you can already see where this is going. Now I spoiled it a little bit, but never mind. So let us plug everything in. We are going to get now the integral from 1/2 to square root of 5/2 of. Now we are going to get r minus 1/2 divided by, and x is the same as r squared minus 1/4. And our differential one form is 2r dr. Okay, this is what we got right now, and this is rather easy to solve actually now that we are here. What you might notice now, if you got a sharp eye, r squared minus 1/4 down here is just a difference of two squares once again. This right here is the same as saying down there in the denominator we get r minus 1/2 times r plus 1/2. This is very fortunate that it is like this, because we can actually cancel this right here out, leaving us overall just with, and 2 is just a constant, so by using the linearity of the integral we can drag it to the front, giving us 2 times the integral of 1/2 to the square root of 5/2. And then we are going to get just, so r in the numerator divided by r plus 1/2 dr. And this is actually really tame now, and we have done several integrals of this form here on this channel already. You can introduce substitutions and so on, so substituting this and getting just an addition of stuff, but we can actually go an easier route here. We can just add a 0 smartly at the top. Doesn't change anything about the fraction, and we can do it in such a way that we can break up the fraction. So by adding plus 1/2 and subtracting 1/2, you're going to notice that we are going to get two fractions. The first one being r plus 1/2 divided by r plus 1/2, which cancels out to 1. This is the first integral. And then negative 1/2 divided by r plus 1/2. Those are our two integrals that we are now going to get and that we are going to break up. Please note that we get a 2 at the front. So by breaking everything up, what we are going to end up is 2 times the integral of this thing right here, r plus 1/2 divided by r plus 1/2, which is just 1, so dr, all in the bounds from 1/2 to square root of 5 over 2. And then we are going to get negative 2 times the integral of 1/2 to square root of 5 over 2. And then we are going to get a 1/2 up here divided by r plus 1/2 dr. And this actually simplifies really nicely a bit further because 2 times 1/2 is just 1. So we can cancel this out. So getting rid of this right here. And by introducing a last substitution, so let's, I'm going to use eta, really doesn't matter, be equal to r plus 1/2 that we got right here. Then by implicitly differentiating, we are going to get that d eta is equal to dr. We are going to end up with the integral of 1 over eta d eta. So just to make everything clear, this right here is just a natural logarithm of eta, where eta is r plus 1/2. So overall, ending us up with, if we integrate the differential one form, we are going to get 2 times r from 1/2 to square root of 5 over 2. And also we are going to get negative the natural log of, and eta, as mentioned before, is r plus 1/2. And all of this in the bounds from 1/2 to square root of 5 over 2. And with this, we are done. So by plugging 1/2 and square root of 5 over 2 into here, the 2 and the 1/2 are going to cancel out. So what we're going to get down here is just, at first, square root of 5 over 2 times 2, which is just square root of 5. And then negative the second part, 2 times 1/2 is just 1. Okay, and also we are going to get negative the natural log of, and then we are going to get r plus 1/2, where r is square root of 5 over 2. So we are going to get the square root of 5 over 2 plus 1/2. And the second part, negative and negative is positive. Logarithm of 1/2 plus 1/2 is just 1. Logarithm of 1, in any case, is just 0. So this right here is actually our final expression. And why did I say that we are going to end everything with a bang? That was already really cool if you asked me, but there's more to it than that. Because if you notice, if we were to bring all of this into the same denominator, we are going to end up with square root of 5 plus 1 over 2. You know this boy, this right here is the golden ratio. So we are going to get the golden ratio phi over here, and the golden ratio phi includes square root of 5. So there's actually one hidden in here too, square root of 5 minus 1. And for this, what we're going to do is, this is just a little detour. I'm gonna put this here because it's not much. As mentioned before, it's hidden in here. Remember, please, that the golden ratio phi is square root of 5 plus 1 over 2. So what happens if we take 2 divided by the golden ratio? This is going to be, yeah, should be 2, I think. 2 divided by the square root of 5 plus 1 over 2. If I remember correctly. Yes, exactly. Then, taking the reciprocal here, we are going to get 4 divided by the square root of 5 plus 1. Now we can rationalize the denominator once again, multiplying both top and bottom by the conjugate, square root of 5 minus 1. So we are going to get overall 4 times square root of 5 minus 4 divided by rationalizing this. So 5 minus 1, which is the same as 4. 4 and 4 is going to cancel out everywhere, giving us overall just the square root of 5. And then minus 1. So overall, and this right here is the banger part, you could say, this expression that we get right here, square root of 5 minus 1, is the same as 2 over the golden ratio minus the logarithm of the golden ratio. And I think this result is extremely golden, like fireworks, a golden result to end the year. And if you want to see more integrals, if you are interested in more STEM stuff, then the contents of today's sponsor, Brilliant, might be a perfect fit for you. Now, fireworks are actually pretty cool in the sense that they make bang as a chemical reaction, so that's cool. But also, if you zoom in a bit further, they actually look kind of peculiar, because the more you zoom in, the bigger the circumference of the structure gets. And this is what we call a fractal in mathematics, just like a coastline. And speaking of fractals, Brilliant has a great course on fractals over in their complex numbers section. Now, Brilliant, with their over 70 interactive courses in all topics STEM, provide the internet community with some of the best online learning content that you can find out there on the internet. It doesn't matter if it's on the go in a mobile app or at home on your PC, just like I do all the time. They get you the best things from both worlds. On the one hand, they provide you with the abstract stuff that you also learn at school and at university, and on the other hand, they provide you with those great visualizations and graphics that you can really use to get a better understanding of the problems at hand and to grasp the topics in such a way that you have never seen before. You don't need to take my word for it. Just see for yourself and check out everything that I put here on screen and have put here on screen up until now. It does look pretty fantastic, right? And it's all over on their website. It doesn't stop. It doesn't matter what you look at, gravitation in physics or Markov chains in stochastics. They provide you with the best stuff that you can actually think of to learn something new on a daily basis. Now that the new year is around the corner, why not give it a shot and see for yourself if you are keen on learning something new on a daily basis by using my link here at the top of the description, brilliant.org/flammablemavs. With it, you are going to get a 30-day free trial of Amazing Awesomeness. Try out the whole landscape of Brilliant for completely free, see if it's something for you, and maybe it fits your New Year's resolutions of learning something new and becoming your best possible self when it comes to learning and just brain capacity overall. And if this feels like it could be something for you for a longer relationship between you and the services, then definitely make sure to use the link in its entirety and get 20% off an annual premium subscription. It's seriously worth it. There's so much going on their website, and they provide the STEM community with more courses over time, all the time. They add new stuff on a day, They add new stuff on a regular basis. It's just an absolute STEM extravaganza, and just check it out for yourself and see if it's something for you. And if you do so, then that would support the channel highly. Also, you can use the QR code somewhere up here in the corner. So check it out, support the channel this way. And I thank you guys for watching me over the years, and especially this last year on YouTube for myself. I'm gonna see how everything pans out, and I'm gonna post more videos starting next year. I'll see about that. I don't know for sure. Other than that, I thank you guys for watching, and up to the next video. I wish you guys a fabulous day. See ya.